Right now, as you are watching this, a hole has opened up in the outer atmosphere of the sun, and the stream of charged particles pouring out of it is on track to hit Earth within hours. NOAA's Space Weather Prediction Center has already issued a geomagnetic storm watch for tonight into tomorrow, July 22nd, and the number driving that watch is genuinely striking. Solar wind speed is expected to more than double from a normal background speed of around 325 kilometers per second to somewhere close to 700 kilometers per second in less than 24 hours. If that speed holds, forecasters say conditions could escalate from a minor G1 level geomagnetic storm tonight to a moderate G2 level storm tomorrow, strong enough to push the northern lights south of the Canadian border into Washington State, Montana, and Michigan, and to light up skies as far from the pole as Edinburgh, Oslo, and the southern tip of New Zealand. And this is not even the most active thing happening on the sun's surface right now. A brand new sunspot region, only cataloged 4 days ago, is already the single most productive flare source anywhere on the disk, and a second older region sitting nearby has grown so magnetically tangled that forecasters consider it the most likely ER eruption. This is why meteorologists and space weather forecasters are calling this the sun's critical week, and it is happening at a moment when our star is still deep inside the most active phase of its 11-year cycle. And, oh hype, no exaggeration, just what the forecasts actually say and what it would mean if the numbers behind them keep climbing. Drop a comment and tell me if you can see the aurora from where you live tonight. I read every one of these. If you want space weather coverage that explains the actual mechanism instead of just showing you a pretty photo of green lights, subscribe. It costs nothing, and like tells the platform to put this in front of more people before the storm arrives. Let us go for 5,000 likes on this one. Thank you. Now let us get into it. To understand why this particular week matters, you first need to understand that the sun does not threaten Earth in just one way. It threatens us in 3 distinct ways, and forecasters track all 3 separately because they behave completely differently. The first is a solar flare, a sudden burst of radiation from the sun's surface that reaches Earth in about 8 minutes, the time it takes light itself to cross the distance between us. Flares are classified by strength using letters, A, B, and C class. Flares are weak background events with essentially no effect on Earth, M. Class flares are moderate and can cause brief radio disruptions on the sunlit side of the planet. And X-class flares are the strongest category that exists, powerful enough to cause radio blackouts across entire regions the moment they arrive. The second threat is a coronal mass ejection, a genuinely enormous cloud of magnetized plasma, sometimes weighing billions of tons, that gets hurled outward from the sun and takes 1 to 3 days to reach Earth, which is why, unlike a flare, a coronal mass ejection can actually be forecast in advance once it is seen leaving the sun. The third threat, and the one driving this week's alert specifically, is a high-speed stream from a coronal hole, a region where the sun's magnetic field opens directly out, into space instead of looping back down to the surface, allowing solar wind to escape at much higher speed than normal, sometimes reaching 500 to 800 kilometers per second instead of the usual 300 to 400. None of these 3 things is the same event, and this week, Earth happens to be dealing with the influence of all 3 at once, though the coronal hole stream is the one arriving first. The story of this critical week actually starts about 3 weeks before today, on June 30th, when an active sunspot region designated AR4479 unleashed an X1.1 class solar flare, the first strong warning sign that this stretch of the solar cycle was entering a genuinely hyperactive phase. What made that event remarkable was not just the flare itself, but what happened in the 24 hours. Immediately afterward, the same region fired off 10 additional M-class flares in a single day, a pace of eruption so unusual that Spassier weather physicist Dr. Tamitha Skov started referring to the region on her public forecasts as a machine gun sun. Several of those eruptions also launched coronal mass ejections toward Earth. And because the CMEs were released so close together in time, some of them caught up with each other in transit and merged into a single, stronger disturbance by the time they arrived, which prompted NOAA to issue a G2 moderate-level geomagnetic storm watch for July 3rd and July 4th. That storm arrived almost exactly on schedule, and then, in the way space weather sometimes humbles even careful forecasters, it turned out stronger than the watch had predicted, escalating into a G3 strong-level geomagnetic storm right on the night of America's Independence Day, and producing Aurora visible across roughly 30 separate U.S. states, far further south than a G2 watch would normally suggest. That gap between the forecast and the actual outcome is worth remembering because it illustrates something important about how these storms are actually predicted. The speed and timing of an incoming disturbance can be estimated fairly well once it leaves the sun, but the single most important variable, the north-south orientation of the magnetic field buried inside the incoming plasma, cannot be measured until the storm is already almost on top of us, at a monitoring point called L1, roughly 1.5 million kilometers from Earth, which typically gives only about 15 to 60 minutes of final warning before impact. For the 2 weeks after that Independence Day surprise, the sun actually settled down considerably. Forecasters described conditions through the middle of July as quiet, with the interplanetary magnetic field weak and Earth's own magnetic field staying. G, calm, sitting at the lowest levels on the standard geomagnetic activity scale for day after day. But quiet on the sun rarely lasts, and on July 17th, a small, unremarkable-looking sunspot appeared near the southeastern edge of the visible solar disk, captured by NASA's Solar Dynamics Observatory before it had even been given an official designation. Within 2 days, before it was even fully rotated into view, that region, now cataloged as AR4491, had already become the single strongest flare producer anywhere on the sun for 2 consecutive days running. Unusually fast escalation for a region that had barely finished forming. At the same time, a separate older region, AR4489, developed what solar physicists call a beta-gamma magnetic configuration, a technical way of describing a sunspot group whose magnetic polarities have become so tangled and compressed against each other that the region is considered mechanically primed to release a significant flare, without anyone being able to say exactly when. As of this week, forecasters put the odds of a common C-class flare from these regions at 50% or higher, with a smaller but real chance of another M-class event, while stating that a major X-class eruption is not expected in the next few days specifically, though that assessment can change within hours if either region continues to grow more complex. And then, arriving on top of both of those active regions, comes the specific event driving today's alert, a large coronal hole stretching across the sun's equator, angled, so that its high-speed stream is aimed almost directly at Earth. The mechanism behind the S kind of storm is genuinely different from a flare or a coronal mass ejection, and it is worth explaining because it is the reason forecasters can give a multi-day heads up for this one specifically. A coronal hole is not a hole in the sense of an empty gap. It is a region where the sun's magnetic field lines not loop back down to the surface the way they do almost everywhere else, instead opening directly outward into space like an unlatched gate. And through that open gate, solar wind escapes far more freely and at much higher speed than the background, solar wind flowing from the rest of the sun. Because coronal holes rotate around with the sun roughly every 27 days, the same one can sweep past Earth's position again and again, which is exactly why this particular pattern was flagged days in advance, rather than discovered only when it arrived. Forecasters at NOAA, at the UK Met Office's Space Weather Operations Center, and independent trackers all converged on the same basic forecast this week. Quiet to slightly unsettled conditions through most of July 20th, then a shift late on July 21st, as the leading edge of the stream arrives, escalating into a period of active to G1, minor storm conditions through July 22nd, with wind speeds potentially reaching G700 kilometers per second at the peak before gradually easing by July 23rd. The most visible consequence of a storm like this one, and the one most people actually care about, is the aurora. And it is worth understanding exactly why a coronal hole storm produces a different kind of light show than a coronal mass ejection does. When charged particles from the sun strike Earth's magnetic field, they get funneled down toward the poles, where they collide with oxygen and nitrogen atoms in the upper atmosphere and cause them to glow. Oxygen typically producing the green and red colors. Most people associate with the aurora, and nitrogen contributing the blues and purples seen in stronger displays. Under normal quiet conditions, that glowing ring sits tucked up near the poles, invisible to almost everyone. During a G1 storm like the one forecast for tonight, that ring expands just enough to become visible from the very northern edges of the continental United States and from northern Scotland, and if conditions reach G2 intensity as some models suggest, visibility can push further south still, into cities like Seattle. There are 2 real obstacles working against skywatchers this particular week, though. First, this storm is being driven by a coronal hole rather than a coronal mass ejection, and coronal hole-driven storms tend to be steadier but weaker than the sudden sharp spikes a well-aimed CME can produce, meaning the display is more likely to be a modest glow than the kind of dramatic display that made headlines back on July, currently the height of northern hemisphere summer, meaning the nights are short and never get fully dark at higher latitudes, and a first quarter moon this week is adding extra light pollution on top of that, both of which make faint aurora considerably harder to actually see with the naked eye, even where the geomagnetic conditions are technically favorable. But the aurora, however satisfying to look at, is really just the visible symptom of something with much larger stakes attached, and this is where the phrase critical week starts to earn its meaning rather than just serving as a headline. All three of the mechanisms driving space, weather, flares, coronal mass ejections, and high-speed streams can degrade or disrupt technology that modern life quietly depends on. Strong flares cause radio blackouts on the sunlit side of the planet within minutes of arriving, disrupting high-frequency communications used by aviation and maritime shipping. Geomagnetic storms of any origin can degrade GPS accuracy and timing signals, which matters far beyond a car's navigation screen, since GPS timing signals are also used to synchronize financial, trading systems, cellular networks, and power grid operations. Satellites in low Earth orbit experience measurably increased atmospheric drag during periods of high solar activity like the one we are currently in, because the extra energy pumped into the upper atmosphere causes it to expand outward, quietly shortening the operational lifespan of thousands of satellites during a solar maximum like this one. And the most consequential risk, though also the rarest, involves the electrical grid itself when a strong enough geomagnetic storm induces slow, direct current-like currents through long high-voltage transmission lines, currents that can overheat and permanently damage the large transformers that keep regional power. Grids running, equipment that is often custom-built to order with lead times measured in months or years, meaning a bad enough storm could, in theory, keep a region without power for far longer than an ordinary outage ever would. To understand what a genuinely worst-case version of this looks like, it helps to go back to the one event every space weather forecaster still uses as the benchmark, a solar storm from September 1st and 2nd, 1859, remembered today as the Carrington event after the British astronomer who documented it. During that storm, the Aurora was so bright that people in the northeastern United States reportedly read newspapers by its light alone, and it was visible as far from the poles as the tropics. Telegraph systems across Europe and North America failed outright. And in a detail that still amazes engineers today, some telegraph operators discovered they could disconnect their batteries entirely and continue sending messages using only the electrical current. The storm itself had induced directly into their wires, while other equipment sparked and, in a few documented cases, caught fire. In 1859, that was largely a spectacle, since society at the time ran on little more than telegraph wires and steam power. A joint 2013 risk assessment by Lloyd's of London and the Atmospheric and Environmental Research Group modeled what a storm of that same magnitude would do to the modern North American power grid, and the range they produced is genuinely sobering. An estimated $0.6 to $2.6 trillion in economic damage, with between 20 million and 40 million Americans losing power for anywhere from 16 days at the low end to as long as 1 to 2 years at the extreme high end, concentrated along the corridor between Washington and New York, across the Midwest, and along the Gulf Coast. The United States National Academies of Sciences separately produced its own estimate, placing the cost of a similar event near $2 trillion. Once disrupted telecommunications, banking systems, and GPS infrastructure are factored in alongside the grid itself. We already have a real, smaller-scale preview of what a partial version of this looks like. In March of 1989, a much weaker geomagnetic storm collapsed the entire Hydro-Quebec power grid in about 90 seconds, leaving 6 million people without electricity for roughly 9 hours, with satellites experiencing anomalies and Aurora reported as far south as Texas and Florida during the same event. And we came close to a full-scale repeat more recently than most. People realize, in July of 2012, a coronal mass ejection of genuinely Carrington-class strength crossed directly through the exact orbital position Earth occupies, missing our planet only because Earth itself had rotated to a different point in its orbit roughly 1 week earlier. Statistically, researchers estimate the odds of another Carrington-class storm actually striking Earth in any given decade at somewhere around 10 to 12%. A low enough number to not be a daily worry, but high enough that multiple national space agencies now treat it as a real, ongoing planning risk rather than a historical curiosity. All of this is unfolding during a period solar physicists call the solar maximum, the most active phase of the sun's roughly 11-year cycle, officially declared by NASA and NOAA to have begun back in October of 2024. Unlike a single sharp peak, a solar maximum typically stretches across a year or more of consistently elevated activity, with sunspot numbers, flare frequency, and coronal mass ejection frequency all remaining well above the quiet baseline levels seen earlier and later in the cycle, before gradually tapering as the sun heads toward its next solar minimum later in the decade. That broader context is exactly why this week does not exist in isolation. The machine gun sun event in late June, the surprise G3 storm on Independence Day, the rapid emergence of an already hyperactive new sunspot region just 4 days ago, and tonight's coronal hole-driven storm are not 4 unrelated stories. They are 4 data points inside the same active window, produced by a sun that is still, right now, near the most turbulent stretch of its natural cycle. So what does this actually mean for you tonight and in the days ahead? If you live anywhere near the northern edge of the continental United States, in northern Europe, or at similar latitudes in the southern hemisphere, it is worth stepping outside after dark tonight or tomorrow night, away from city lights, and looking north, since a genuine, if modest, chance of aurora is on the table through July 22nd. If you do not see anything, do not assume the forecast was wrong. Short summer nights and this week's moon are working against visibility, regardless of what the geomagnetic numbers do. Beyond the aurora itself, if you work in aviation, GPS-guided agriculture, or anything depending on precise satellite timing, it is worth knowing that NOAA's Space Weather Prediction Center publishes free public forecasts the same way the National Weather Service does for ordinary weather, and checking it during a stretch like this one costs nothing. The bigger picture lesson from this particular week is not that at Carrington level, catastrophe is imminent. The specific combination of speed, orientation, and direct hit required for that remains rare. The lesson is that our technological dependence on GPS, satellites, and interconnected power grids has grown enormously since the last truly severe storm hit us in 1859, while our infrastructure's actual hardening against that risk has grown considerably more slowly, which is precisely why space weather agencies around the world now treat weeks like this one as worth tracking in real time, rather than waiting to react only once something goes wrong. To bring this all together, the sun is entering this stretch of days already primed by a month of unusually high activity, starting with the machine gun sun eruption of 10M class flares in a single day back on June 30th, followed by a geomagnetic storm that outperformed its own forecast on Independence Day, followed by the rapid 4-day emergence of a brand new region that immediately became the sun's most productive flare source, and now capped by a coronal hole stream expected to more than double solar wind speed and push geomagnetic activity to G1, possibly G2 levels through July 22nd. None of this guarantees a major event. Forecasters are explicit that an X-class flare is not expected in the immediate days ahead, but it does mean the underlying conditions for one, an active sunspot region, with a genuinely tangled magnetic configuration, are sitting on the disk right now during a solar maximum period that NASA and NOAA say is still ongoing. Behind every one of these technical terms sits a real, practical stake, a farmer relying on GPS-guided equipment during harvest season, an airline rerouting a polar flight path around a radio blackout, and a grid operator somewhere along the Washington to New York corridor watching a geomagnetically induced current reading tick upward on a control room screen, all connected to the same sun that, tonight, might also just give you a faint green glow on your northern horizon if you are willing to step outside and look. We are going to keep tracking this the same way we did today, straight from NOAA's Space Weather Prediction Center, the UK Met Office, and NASA's own solar imaging, not recycled Aurora photos with no forecast behind them. Subscribe if you want to know the moment either of these active regions actually produces something bigger, because based on how quickly AR 4491 went from unremarkable to the sun's top flare producer in under 2 days, it likely will not take long. And leave that comment below. Tell me whether you caught anything in the sky tonight and where you were watching from. 5,000 likes on this one. Let us go. See you in the next one.